All right, welcome everyone to the Hot Electronic Seminar Talks. This is the fifth talk of spring 2020. I think there's not much more for me to say, but just to introduce the speaker. And I think I know how to pronounce his last name better than the speaker for some reasons. So I'll obviously try to mispronounce it the best I can, but the same way I try to mispronounce my own name. And so, yeah, so I'll do my best. But yeah, it's a great honor to introduce today's speaker, Denis-Charles Cisinski, whose topic today is the univalence of the universal coCartesian fibration. Thank you.
So thank you very much for the invitation, and I'm very happy to give a talk in this seminar. This is a report on a joint work still in progress with Kim Nguyen. The goal is to speak of the universal Cartesian fibrations. So if you learn category theory, classical one, or infinity category theory, a fundamental construction is the correspondence between coCartesian fibrations and functors with value in the category of categories, so it is so functors from A to the category of infinity categories correspond to fibrations to A, and taking A to be the infinity category of infinity categories itself. This gives rise to universal fibrations, and which is the object I want to discuss today. So quick observations about how to make sense of this. In practice, so we have one category of infinity categories, but to define this correspondence, we have actually to define an infinity category of infinity categories, which could be challenging depending on your on the way you define this kind of objects. And then you have several ways to think of this equivalence. Once it is an infinity categories, and you could look for an equivalence of infinity categories or an equivalence of groupoids. The groupoid version will correspond to what topologists are used to. It corresponds to study moduli problem. It's a moduli problem of classifying Cartesian fibrations. So all these topics have been discussed, in fact, are at the heart of the theory of infinity categories that you can find in the book of Lurie, for instance. But with the approach of Lurie, so the basic tool is a rectification procedure defined through the homotopy current nerve, which produces an equivalence between the category of simple sets and therefore of the full subcategory of infinity categories defined as quasi-categories, for instance, and the category of simple categories, which are stricter objects. And then for each simple set, in fact, we define a model structure of on marked simple sets over A, whose fibrant objects are the coCartesian fibrations, and then we produce a Coulomb equivalence between the model structure of coCartesian fibrations, or corresponding to them, and the model structure of simple functors, enriched functors from the category, the simple category defined by A, with value in simple sets with some projective or injective model structure. And once all this is settled, then you can start, and of course this produces a lot of rectification procedures, and then you can produce this straightening and straightening in the form of a Coulomb equivalence, and then you can translate that into an equivalence of infinity categories. But then, so we are in a situation when the homotopy current nerve plays a central role. And so what I would like to discuss today is another approach to exactly the same thing, but avoiding any kind of homotopy current nerve. I should say that one of my goals is really to have a general approach of the theory of infinity categories. And there is of course an approach of real and verity, which is quite advanced, with a book already there. But in there already, the straightening is also used the homotopy current nerve, which is different from what we are discussing today. At least literally. Of course, the two equivalence, everything is the same. And so you see the way I introduce it. So we have the straightening, and then we can deduce the Cartesian fibration to begin with. So what I would like to do is to do a converse. I would like to start with a universal coCartesian fibration and to see how we can deduce a straightening correspondence from it. And in fact, the reason why I want to do that, one of the reasons actually, it's not the only one, but it is a way which is compatible with the spirit of the theory of dependent type theories. And so it means I would like to describe the theory of categories or of infinity categories using dependent type theory, or at least a fragment of it. So I'll try to be slightly more precise about that now. Not very precise, but a little bit. So the idea is that if you look at the semantic interpretation given by the Joyal model structure, so the theory of quasi-categories, they form a tribe in the sense of Joyal. So it is obviously a setting where you can interpret the language of type theory. But the point is that we have dependent sums, but we don't have all dependent products. And in terms of categories, this is reasonable because the functors for which dependent products exist have a name, and they are called Conduchet fibrations. And there are explicit examples of functors which are not such things. If you think of in terms of model structure, it's well known that the Joyal model structure is not right proper, and that means the fact that we don't have all dependent products and the fact that all functors are not Conduchet, in fact, is reflected by the non-properness of the Joyal model structure. Okay, but there are functors which have dependent products, and they are actually very important, instrumental in the development of category theory. So a large class of examples is provided by coCartesian fibrations or fibrations. And a very other important example, which is not fit in this class, is the inclusion of the boundary of the interval. And it is very important because the dependent product along this map is precisely the join operation, which gives rise to slice, co-slice, and so forth. So many of the features of category theory are really determined by this language of dependent type theory with only dependent sums and only dependent products for a reasonable class of maps. And then it means also that because we have a big hierarchy of kind of fibrations, you could have discrete fibrations, Cartesian fibrations, coCartesian fibrations, and so forth. It means, in fact, you have a hierarchy of deduction rules, not only one deduction rule, but many kinds of such things. Okay, and if you want to develop such a formalism, so we could also so I won't give a full setting of axioms today, but I will instead I could also express what should be the goal of or a possible goal of a theory of category theory or a formalized version of this using dependent type theory. It means you want to produce theorems of the form the theory of pointwise kind extensions, limits and colimits. And using that, you should be able to produce a homotopy theory, that is, you want to understand how to invert maps and then how to deconstruct the Rai functors as kind extensions and so forth. And eventually also to define presentable categories and higher topoi. And so the goal would be eventually to have a very formal approach to all these kind of things. And so it could be a course description of the main goal of a directed homotopy type theory. Just also as a side remark, so if we have a dependent type theory, so we always have one category of types. And that fits with, I think, with Lovier's point of view that in the theory of categories, there is really one category of categories to begin with. Okay. So now I will start to go to the core of the subject. So I will work mainly with quasi-categories, so sumptuous sets satisfying the Segal condition in a weak form. And so, as I sketched, or as I said very early on in the introduction, so to define coCartesian fibrations, it's good to see them as fibrant objects somewhere. And so the way to do that is to play with Marx sumptuous sets. So sumptuous sets equipped with a set of edges, and so that any degeneracy is part of this collection. And so for getting this marking, have two adjoints. A right adjoint, which is defined by this sharp sign. So A sharp is a sumptuous set A together with all edges. And so I will sometimes write the slice category of marked sumptuous set of this A sharp are just marked sumptuous set of A. So by default, everything is marked. And there is also a left adjoint, which consists in adding the minimal a set of edges. So it is a C flat. So to C, we assign C flat. And a very well-known theorem is that there is a unique model structure on the marked sumptuous sets of a sumptuous set A, whose cofibrations are monomorphisms, and whose fibrant objects are precisely the coCartesian fibrations. And so this is called the coCartesian model structure. And dually, we can do a version with Cartesian fibrations. And of course, taking the opposite operator defines an equivalence between the coCartesian fibrations over A and Cartesian fibrations over A up. And also, so I didn't write it, but you can do that over any marked sumptuous set. And then it's just that you will speak of coCartesian fibrations which are defined only relatively to the marking. It means you can only lift marked. You can find coCartesian lifts over marked edges only. But this is a very technical thing. So let's think just of coCartesian fibrations over any sumptuous set. And this sumptuous set A, so you should think of as a quasi-category. So there is a technical way to think of this. You would like to describe the fibrant objects and the fibrations between fibrant objects very explicitly by explicit lifting properties. And so one way to do that is to find generators or a class of anodyne extensions. And one such thing can be defined as the smallest saturated class of maps in marked sumptuous sets containing all the flatification of the inner horns, the canonical map from the J flat to J sharp with J the working isomorphism. And then we like to lifting property, which essentially says that coCartesian lifts of edges exist and are unique. And so we call this saturated class the class of marked left anodyne extensions. Because if you do the analog thing without marking, it really gives you exactly the class of left anodyne maps. And so its proposition due to Kim is that for any sumptuous set, so any marked left anodyne extension is a trivial cofibration for the coCartesian model structure of anything. And furthermore, the fibrant objects and fibrations between fibrant objects are completely characterized by the Raff lifting property against this marked left anodyne extensions. And this precise knowledge is instrumental to prove this kind of theorem. So it's a theorem due to Lurie, which is that, for instance, pulling back weak equivalences of the Joyal model structure induces a Coulomb equivalence of coCartesian model structures. And so, because as I said, I would like to get rid of approach using homotopy current nerves. So this precise description of the left anodyne extensions and of fibrant objects and fibrations between fibrant objects is a way to prove this kind of theorem, avoiding homotopy current nerves. And the core of the proof consists in studying the particular case of the inner horn inclusions. This technical thing about the coCartesian model structure is also instrumental to prove the following theorem of Lurie, which is that for any Cartesian square of some sets, where P is a coCartesian fibration, is actually homotopy Cartesian in the Joyal model structure. You see, as I said, the Joyal model structure is not right proper, but this theorem is in fact a way to say that coCartesian fibrations are conjugate fibrations in the setting of infinity category theory. And so this is a theorem of Lurie that you can, proof of which you can find in higher algebra. But again, the proof of Lurie uses in some places homotopy Kortner, and so it's a slightly different approach that we have. And another thing which is related to this section of Lurie, but it's not explicit there, is another theorem of Kim that pulling back along the Cartesian fibrations give you a left Quillen functor at the level of coCartesian model structures, where here you have to take the, as marking, you have to take only the coCartesian edges on the domain of the fibration. And an important corollary of this theorem is that the evaluation at an object, which is actually a right Dirac functor, so it commutes with homotopy limits on the nose, but it's not formal that it would commute with homotopy co-limits, but using this this theorem that pulling back along a Cartesian fibration, you can prove that the evaluation commutes with homotopy co-limit because you compare with pulling back along a slice. And then using this theorem, it's quite easy to have a proof of the corollary. So that is an important technical device. Now we can come back to the problem of constructing universes. So we have to fix the notion of size. So an inaccessible cardinal or Grotonic universe in order to make sense of the notion of small set. And then we can define a simple set. So in a way which is very well known in the community of dependent type theory. So whose simplices are over data n are maps to data n equipped with choices of pullbacks. And possibly with a normalization like this. And then you can define another central set, the pointed version. It means you also consider such data together with a section of the map P as above. And then you can forget the section. It gives you a map. And this map is in some sense a universal map of simple sets, with a small fiber. So concretely, it means that for any map with small fibers, to define a collection of pullback squares over any simplex with a small fiber is really equivalent to define an actual pullback square from this universal map. Okay, and then the idea to construct universes is consist in producing a subobject of this U, and then to take the pullback. And the only property, so I can come back to the slide. So you see, if you have a notion of fibration, which is determined by what it does on pullbacks of each simplex, then it gives you a well-defined subobject of U. And this is the case for any kind of fibration we use in infinity category theory. So for coCartesian fibrations, left fibrations, and so forth. And so that's why also we can define this hierarchy of universes. So we have the universal map with no constraints. Then we have a universal coCartesian fibration, which I denote a map from infinity cat pointed to infinity cat. But for the moment, it's very formal. And this is just a notation for assumption sets. We don't know that it is an infinity category of infinity categories yet. And then the groupoid version is a universal Can fibration. And then there is a further version with a small k. So k of C for a quasi-category is for the maximal Can complex. So it means the same object, but you take only invertible one cells and then keep everything else the same for higher cells. So somehow we can prove that the left-hand side is really the universe defined by Voevodsky, up to slight technicalities. And you can prove that the middle one, I mean, the one from quantum infinity groupoids to infinity groupoids is a univalent left fibration with a codomain, which is an infinity category of infinity groupoids, which I did in my book on higher categories. And then because the left fibrations are conservative, so it really says that the left-hand square is a pullback square. And so in particular, all the properties you prove for the universal Kant fibration give you the property of the Voevodsky's universe. But the difference, you see, is that we have the middle map to infinity groupoids is really a Kant fibration, but not of a Kant complex. It's of a quasi-category. That's slightly different. So it's really about locally constant functors. So the idea is that we would like to do the same for the right-hand side, for the universal coCartesian fibration. So what Kim and Nguyen did in his PhD thesis was I mean, among other things, is that was to prove that the codomain of this universal coCartesian fibration is indeed an infinity category. So it means that the zero cells are obviously infinity categories. So it means it is really an infinity category of infinity categories. And then the question is to wonder if it is the right one. That is, you would like to understand if the maps, the mapping spaces in this infinity category are the correct ones. But we could come back to the proof of the theorem that it is an infinity category to begin with. And so somehow that's very similar to Voevodsky's proof of the fact that the universal Kant fibrations between Kant complex is the one he defined. So the idea is simply to say that if you have a coCartesian fibration of in a horn, you can prove it is a pullback of a coCartesian fibration defined on the whole simplex. And the idea is to prove that you have in fact an homotopy pullback using, you have Quillian equivalences, and then you can use minimal fibrations. Just to also for a comment for those who know this kind of thing for classical dependent type theory, the problem is that we don't have right properness, so we cannot play with the fact that taking dependent product preserves fibrations of some kind. I mean, at least it's not obvious at all that it would work. So for the moment, I don't know with this kind of approach how to get rid of minimal fibrations so far. But that's really otherwise rather standard methods. But using this model structure of Mark-Sumshaw sets. And as I said, then the next goal is consists in determining the mapping spaces. And so the observation is that the category of Mark-Sumshaw set is enriched over Sumshaw sets over A. You can describe this in terms of dependent product of some kind, and then sub-objects of these. And then you can check that for two coCartesian fibrations, P and Q, so from X to A and from Y to A, respectively, are the maps from X to Y over A in this setting. So we are the coCartesian functors, essentially by definition. And then, so I note cocart A from X to Y is this home. And then there is a sub-object of invertible such maps, so fiber-wise invertible, if you wish. So it means that so cocart A from X to Y is actually equipped with a map to A. Yeah, it's really some set over A, and a functor from anything, any object B to this category is the same thing as a map to A, together with a map, a coCartesian functor between the pullbacks of a B. Really, essentially, by definition, that's a way to define it if you want. And take this as a definition and then prove it is representable. And then you can check using all this property about nice properties. We know the homotopical property of pulling back along Cartesian or coCartesian fibrations. You can deduce that these two functor to the base from the category of coCartesian maps to A and from the subcategory of equivalences to A are isofibrations. So in particular, this category of coCartesian functors or invertible coCartesian functors are infinity categories whenever A is, in particular. And then it's time to look at examples. And so so we have this infinity category of infinity categories, and then we can take the product. And over the product, then we have two canonical coCartesian fibrations, which I called with a 1 and a 2. So it means I will just pull back along the universal one along the two projections. And then if we pull back further to the category of coCartesian functors from ket1 to ket2, then we have a universal coCartesian functor over it. And then if we pull back further to the subcategory of, or restrict to the subcategory of invertible coCartesian fibrations, then we have the universal invertible map.
Sorry, can you just go back? Those slides were
yes.
Too quick. Can you go back 2 slides and just
this one?
Again? Yeah. Like what are, I didn't catch what these XIs were.
So what are the, so there is a universal, so I should come back to the, there is a universal map, a coCartesian fibration with small fibers, which is, I denote the map on this, for infinity cat pointed to infinity cat. So this is a coCartesian fibration. And then if I come back to the product, then because I have two projections, I can pull back this universal coCartesian fibration, and then these are the two arrows you see here.
Okay, good. And then the next, the XI, the X1 and the X2.
And then you have so this the bottom on the triangle goes to this product, yeah, because it is coCartesian fibration between these two things. Yeah, you have to remember that if you take cocart A, it lives over A. Yeah. So the cocart from cat1 to cat2, it lives over the product of infinity cat with itself, and therefore you can pull back cat1 and give you x1, and you can pull back cat2 and give you x2. But then, essentially, by definition of this coCartesian thing, you have a universal map between this. This is a universal coCartesian natural transformation between coCartesian fibrations.
Okay, thank you.
It is defined by the identity of the, yeah, if you remember this slide, so you have to take, here you take A to be the infinity cat times itself, and you take the equal, you take B to be equal to cocart of that, and the left hand side you take the identity and give you something on the right hand side, and that's the map from x1 to x2. Okay, and then if you restrict to the sub object of equivalences, it gives you y1 and y2, and then it is a universal equivalence between coCartesian fibrations. And so a way to express univalence is the fact that, so there is a map from infinity cat to there, because you see, so it means that to have a map to this equiv infinity cat times infinity cat of cat1 to cat2 is really the same as having an equivalence between two coCartesian fibrations over yourself, whatever you are. And so in particular, since the identity is such an equivalence, this defines a map. And so the univalence can be described by saying that this map is a trivial cofibration. And or another way to say it is that the object from equivalences between the two universal coCartesian fibrations is actually a path object of the infinity category of infinity categories in the Joyal structure. Because you see, you should have a map to the product, and so that's really the definition of being a path object. It's a weak equivalence to it's a factorization of the diagonal into a trivial cofibration and then a fibration. And the map to infinity cat times infinity cat is an isofibration. That is a fibration for the Joyal structure because of the last line of this slide. Yeah, so all the maps are isofibrations. The maps to A here. So here A would be infinity categories times itself. Okay, and then the proof. I mean, I won't do it here, but it's really it follows essentially the same pattern as the proof, Voevodsky's proof of univalence. Okay, so what this means, this univalence, is that it is already a kind of straightening and straightening, but in the moduli space version. So from there, you can deduce that you have if you fix infinity category A, the moduli space of all coCartesian fibrations of A is really equivalent to the moduli space of all functors from A to infinity categories. Okay. So, but if you want to do so, there's a way to do straightening and straightening. But if you want the full version, so you don't want only an equivalence of infinity groupoids, but really an equivalence of infinity categories, which is what I will try to discuss now. For that, we need a little bit more technical results about the model structure, the coCartesian model structure. So if you fix one category, and so I will know the same way the category in its nerve, then you have the category of functors with value in simple sets, and the category of marked simple sets of A, where A is equipped with the full marking. You mark everything. And then you can check that there is a unique continuous simple functor, so continuous in the simple sense, which sends an object to the co-slice or the nerves of the co-slice, which would be a left fibration and therefore coCartesian fibration. And then you can prove that this functor is actually a left Boolean equivalence from the injective model structure on the left-hand side. So I should have said with respect to what. So you have to take the Joyal model structure on simple sets, and then you take the injective model structure with respect to that on the left-hand side, and the coCartesian model structure on the right-hand side. Okay, and for the proof, it's not super hard once you know that evaluating, taking the fiber of a coCartesian fibration is commute with homotopy co-limits. You see on the left-hand side, so the evaluation commute with homotopy co-limits. Essentially, by definition, you preserve representable functors, or maybe here co-representable functors on the nose, essentially by definition. And so on what wants to be a representable functor, you control perfectly what you are doing. And then you want to say that everything is a co-limit of representable functor, and therefore that you are done. But for that, you have to some compatibility with co-limits to check. And that essentially this result, I said at the beginning, that evaluating at the fiber of coCartesian fibrations commute with homotopy co-limits. And then that's a very easy result. And so the corollary is that once you have a Boolean equivalence, then you can go to injective model structure everywhere. And so for any other one category B, you have an induced Boolean equivalence between functors from B to the category of functors from A to subsets sets, equipped with a triangle structure of subsets sets with injective model structures. And then the injective model structure from the category of functors from B to the coCartesian model structure of A. And maybe just as a remark, this proposition in the unmarked case, I think, can be found also in a paper by Mordijk and Hertz. And but the proofs are very similar. And yeah, okay. So we have this, and so that's really a kind of a rectification procedure, because you see, in particular, you can take A to be delta 1 maybe. So it really says that correspondences between marked correspondences or between coCartesian fibrations really correspond to natural transformations, at least up to equivalence in a suitable way. Okay, then to compare, so I would like to produce an equivalence of infinity categories. So I have to produce a comparison functor, and for this, so we use the definition of the infinity category of infinity categories we had, that is through the notion of universe. And so there is a universal coCartesian fibrations in the category of one categories. So here the cat pointed is a category of pointed categories. So category is equipped with an object, and maps are functors which preserve the base point, but in a lax sense. So you don't preserve the base point on the nose, but you have a one cell or a path comparing them. So maps in pointed categories are really pairs of functors and one cell comparing what happens to the base point in a correct direction. And it gives you a coCartesian fibration, which is in fact the universal one. If you want to play this game of universe for coCartesian fibrations for one categories, and then if you take the category of simplices, the full subcategory, you can restrict these coCartesian fibrations over there, and then taking the nerve, it gives you a coCartesian fibrations over the nerve of delta, and therefore a map from delta to the infinity category of infinity categories. And then, so a corollary of, so here I'm going a little bit quick, but a corollary of the fact that we have already the univalence and the Coulomb equivalence we had on the previous slide already, is that you can prove that the category of infinity categories has colimits, and therefore you can produce the left-hand extension along I, and then give you a co-continuous functor from so from precision of a delta in the sense of infinity category, so precise value in infinity group weights, and then of course they contain as a subcategory precise value in sets, which are actually sumptuous sets. And so restricting this extension of I to sumptuous sets gives you a functor which I call gamma. Then, so using again the straightening, and together with so a little bit of theory of infinity categories, so you are supposed to understand can extensions and maybe how to do homotopy theory. I mean, how to interpret homotopy theory within infinity categories. To interpret, but so you can prove that this functor gamma sends weak equivalences of the Joyal structure to equivalences, and that it sends push-outs along monomorphisms to push-outs of infinity categories, and also commute with small sums. And out of that, if you formally you can deduce that gamma give you an equivalence of one categories when you truncate, when you go to the, so so what I write on the slide on the first point doesn't look correct. So what I meant is that if you invert the equivalences of the Joyal structure in sumptuous sets on the left-hand side, then gamma will induce using the third assertion a colimit preserving functor, and what the fourth assertion is supposed to mean is that this induces an equivalence of one categories when you take you apply the functor tau, which is the left adjoint of the nerve, and because it's known that if you have a functor like this, which commute between infinity categories which are co-complete and commute with colimits, if you have an equivalence of one category, then it is an equivalence of higher categories. And therefore, you get the following theorem. So you get it means that, so if you denote by L the procedure of inverting weak equivalences in the model structure, but in the sense of infinity categories. So for any one category A, if you take the model structure, or the injective model structure of functors with value in the Joyal structure, it will be equivalent to functors from A to the localization or the homotopy infinity category, if you want, of the Joyal model structure. This is for formal reason. It's true for any model structures, this first equivalence. And then the second equivalence, it corresponds to the previous slides. And for the second equivalence, you only need to prove the case where A is actually the point. And then that is already a way to do straightening and straightening. And then using the fact that any infinity category is a localization in the sense of infinity categories of one category, then using this theorem, it's easy to deduce that for any simple set A, in particular for any infinity category, if you take the localization in the sense of higher categories, or the hierarchical localization, if you want, of the covariant model structure of A, then you get an infinity category which is equivalent, which is equivalent, no, it's not equivalent, but really equivalent to the infinity category of functors from A to the infinity category of infinity categories. In particular, so the mapping spaces, in fact, the internal home of the infinity category of infinity categories are really the correct ones. And so that is really a way to say straightening and straightening. That is a new proof of it. And now I would like to finish. So I'm being very, very quick. So I would like to finish with as another interpretation of these results. Because as I said, I'm also interested in the despondent type theory interpretations of it. And we could formulate theorem of the form we just saw before, but it's not complete to me. It's not clear to me that it is reasonable to really speak of a localization of a one category giving rise to a type or something. So I don't really even know what that means exactly. So I'd like to reformulate this straightening in a different way, which is related to univalence, I think. So there is a universal coCartesian. There is a universal coCartesian functor between coCartesian fibrations with small fibers. And so that determines a coCartesian fibration over delta 1. Again, what I'm saying here is that I have to come back a few slides before, which I will do. If you remember what we have here, so we have a map from x1 to x2. And if you take A to be equal to this to the bottom of this triangle on this slide, and you apply, for instance, the Boolean equivalence defined by this proposition, at least up to equivalence, but in a way which is well defined up to equivalence, uniquely, like you have a contractible space of choice, something like that. So this map from x1 to x2, it really corresponds to a map between the corresponding functors, which are classified by this. And so, this map from x1 to x2, it really corresponds to a map between functors to the category of infinity categories, and that really means a map from the delta 1 times this big thing, the infinity, the category classifying all coCartesian maps, and then by transposition, this defines a map functor from this infinity category of coCartesian transformations to the infinity category of arrows or category of functors, if you want. That is the internal home from delta 1 to infinity categories. That is a map like this, and then you can interpret straightening and straightening as an equivalence like this. And this equivalence, I think, deserves to be called a directed equivalence because it's in fact a directed way to do univalence, because if you restrict to invertible transformations, so invertible transformation gives you sub-objects on each side of the equivalence. So you will have invertible functors on the right hand side, and then you would have on the left hand side you would have what I call the equiv over infinity cat times infinity cat. So the universal equivalence, and as I said, the universal equivalence. So here, the fact that this is the classical univalence for the universal coCartesian fibrations can be really formulated into an equivalence between the left hand side. So here this equiv infinity cat and himself and so forth, with the full subcategory of equivalences in infinity categories. That is the full subcategory of fun delta 1 to infinity cat whose objects are invertible or whose objects are equivalences of categories. And that this is really equivalent because you just have the 2 out of 3 property for equivalences. And so the map for the category of infinity categories goes in the two objects as trivial cofibrations, and therefore, I mean, this is really equivalent to that. And so this equivalence can be really promoted to an equivalence between these functors. And I would like to emphasize that from these two equivalences only, you can really reconstruct the classical straightening and straightening. Although in practice, I only know how to deduce these equivalences from straightening and straightening. But from a dependent type theory perspective, I think this formulation is interesting because it is type theoretic. If you try back home slowly to unpack everything, you can really express all these objects using only the language of the dependent type theory. So it would be a way to formulate some kind of axioms. So I was very quick, but I think I finished now. So I thank you very much for your attention.
Right. Thank you very much. That was great. So let's thank the speaker. We're going to do silent applause, so we're not unmuting anyone. But my apologies. But we're clapping.
Okay.
Just because it tends to mess up microphones. And I'm going to open the floor for discussion. I think we're going to have some questions, comments, anything is invited. So just unmute your microphone and ask the question. So.
Okay.
I hear someone.
All right, I'll go first. Firstly, this is really nice. Thanks very much. And I'm also a big fan of your sort of exposition of the universal left fibration in your book. So it's great to see that extended to the coCartesian case. I guess I had so if you could go back a few slides to where you were defining the functor gamma. I mean, yes. Something in there, it seemed a little bit reminiscent of the way that Barwick and Schomer-Priest think about a model of infinity n categories as a localization of simplicial presheaves on Gaunt, which I think in the case n equals 1 is just delta. Yes. Is that sort of a kind of a similar construction of, I guess you described this as an equivalence of from the one category of the homotopy category of the Joyal model structure to this one category, but
yeah, it is definitely related. I mean, or the same, I guess.
Okay.
Yes.
Yeah. So then, I guess my other question is, if we're going back to ordinary one categories, the straightening and straightening, the Grothendieck construction is actually an equivalent to two categories rather than infinity one, and it's not been clear to me kind of the simplest way to enrich this one step further from the moduli space level through the infinity category level to some sort of infinity two category level. Do you have any thoughts on that?
No, as I said, I mean, I think very one categorically, so I can't claim I have a solution for that. So I have nothing better than to say than that, and then I have an equivalence of categories, and therefore the internal home correspond, but I don't know.
Sure.
I mean, yeah, in some sense, well, to be able to understand the answer to this question, I would like to develop the theory of infinity two categories for real, which I've never done.
Right.
So I cannot say I can. I know how to do that. So I think it would be very worth doing that. And actually, I have a student who I push to go in this direction. So I really very interested in there to develop infinity n category theory, in fact. But I think n equal 2 would be good, and then to understand this kind of issue. But so in some sense, you see, if we wanted a full flavor of that, we would like to say we take the theory of coCartesian fibrations over infinity 2 category. You see, like in some way, like what I do in my book, I do left fibrations over infinity 1 categories or can fibrations over such things. You see, so to go to infinity 2 to have the full flavor, I think we should. It means we want to understand coCartesian fibrations over 2 categories, and then and even if you don't do infinity 2, actually, you just do ordinary 2. I guess it's yeah, you have to spend some time before you understand everything. I guess to understand the Grothendieck construction perfectly and so forth. At least I do.
So maybe I'll frame. I get the next thing is sort of a comment, but I'll frame it as a question for your student, perhaps. So there's a particular example of a fibration of infinity 2 categories, and I'm going to mean infinity 2 category in a very strict sense, which I'll explain in just a second.
Okay,
and I'd love to understand its relationship to the universal coCartesian fibration defined here. So the base is the infinity 2 category of infinity 1 categories, but let's just say it's quasi-categories as a quasi-categorically enriched category. So I'm working at the point set level. So quasi-categories is enriched over itself. So it's an infinity 2 category.
Yes.
So that's the base of this Cartesian fibration of infinity 2 categories I'm about to describe.
Yes.
And then the total space is, again, it's a quasi-categorically enriched category. That's the sense in which it's an infinity 2 category. And its objects are coCartesian fibrations of quasi-categories.
Yes.
And then the mapping quasi-categories are, it's like you described, it's the quasi-category of coCartesian functors. But I allow a map between the base two. So these aren't just triangles, they're squares.
So you do again a Grothendieck construction of all, yes, is what you mean? Or?
So I'm just working at the point set level. So inside the simplicity enriched category of quasi-categories.
Yes.
So you can define from that a new simplicity enriched category whose objects are coCartesian fibrations with an arbitrary base.
Of any base is what I mean. Is what you're letting the base vary or something.
Yes, the base varies.
Understood.
Right.
Okay, understood. Right. Okay,
yeah, the base varies. And so you have the codomain functor between them.
Yes.
And you can show that codomain, so it's a functor of quasi-categorically enriched category, so it's an infinity 2 functor. And you can show that it has properties that you'd ask to say that's a fibration of infinity 2 categories. So it's locally a fibration. If you restrict to 2 objects, you get a map now, quasi-categories, that's a coCartesian fibration. There's some Cartesian functor when you sort of whisker, pre or post whisker, that's some property in the, say, Buckley notion of fibration of 2 categories. And then there's this global property, which is the pullback stability of coCartesian fibration. So if you have a coCartesian fibration and an arbitrary map in the base, you pull back, you get a coCartesian fibration.
Yes.
So this is one of the dual notions of fibration of infinity 2 categories. And I'd love to understand its relationship with this universal coCartesian fibration as infinity 1 categories.
Understand? Yeah, but I have no direct answer to that.
Yeah, sure. Well, anyway, maybe mention it to your student.
Sure, I will.
All right. Any other questions? Comments? Oh.
Yeah, Ezra Getzler. Shall I go ahead?
Go ahead. Yeah.
Yeah. Okay. Hi, Denis-Charles. Long time no see. So I'm going to read your talk very naively. I'm not a homotopy type theory person, as that your directed univalence is in some sense equivalent to axiom of choice because of your invocation of minimal fibrations.
So sorry, is that could you repeat again?
Your directed univalence theorem from like slide 10 or something.
The last one, yes.
Is equivalent to axiom of choice.
Is that a question or?
No, it's my reading of your talk. So let me. So my question is, where does axiom of choice enter into Lurie's straightening and unstraightening?
It depends what you mean by axiom of choice, or
the existence of minimal fibrations.
Yeah, no, the proof. Yes, sure. But
so the existence of minimal fibrations for me is the axiom of choice.
Yeah, that is true. I mean, of course. So in the proof, I use the axiom of choice.
That's right. So I want to reread your. I don't know. Maybe your theorem is weaker than the existence of minimal fibrations, but let's suppose it's equivalent. Then it's a reformulation of the axiom of choice from my perspective. And then and what I'd like to know is where that enters into Lurie's treatment of straightening unstraightening.
Yeah.
I'm drawing a blank. I mean, maybe he invokes just the existence of the Quillen model category structure, which also requires.
Yeah, he goes through model structures all the time. With,
so I see. So maybe you could say that your theorem is a crisper invocation of the existence of minimal fibrations than running the whole Joyal Quillen model structure.
I mean, the interest of formulating things in type theory is that you can implement the language in many other settings.
Yes.
In particular, for instance, you could take your favorite topos or infinity topos, or I don't know what you like, but then you could do everything internally to the topos. I think about the axiom of choice, and then you see, then you are supposed to quit a little bit axiom of choice, at least in some way.
Yeah.
And then the way I formulated the directed univalence is true. You see, so at least that is the interest of it is that you see in the proof, so the previous slides, then I use very much the axiom of choice, and all this, but the last the reformulation, what I call directed univalence, is good because at least the way I formulate it, it will be true in any topos.
I see.
Even though and in the proof I will use axiom of choice, but I don't care. It will be true in any topos.
yes. Yeah. No. Okay. Very good. Yeah. Yeah. Is that in some sense? Could I ask, from an old-fashioned perspective, is that something like Boolean localization? You prove something in a Boolean localization, and that then you can then reflect it back into the original topos.
But that would be a way to prove it. But we could also hope for methods which avoid it. I mean, if we take the non-oriented version of univalence, people from the homotopy type theory communities, there are plenty of proofs approach to the model structure for sumptuous sets, and approach to univalence for cubical versions and so forth, which are completely constructive. And so
absolutely, yes.
It's not because I use axiom of choice myself that we have to.
Yes. No, my question is, in some sense, is it absolutely essential here? Unlike in the unordered version, that's, I guess, for the future to determine. Yeah. Thank you.
You're welcome. Thank you for the question.
All right. More questions?
Yeah. Something I was curious about, and forgive me, you might have made a brief reference to this during your talk, but do you have any thoughts on what kind of syntax of a type theory this directed univalence in quasi-categories might give us semantics for?
Yes, that's something I plan to write down. I mean, so I can, with words, I can say. So I take dependent type theory, but as I said, I don't introduce dependent products everywhere because I don't want that. We can, I mean, you see, there are two approaches. Either you say, okay, I embed this into a big classical dependent type theory. That will be the point of view of Schulman-Riehl, for instance. So you have and then you want a language of cubical sets or sumptuous sets, or cubical something, say, or sumptuous something, and then you formulate that you restrict to some types of somewhere, so and so forth. But the way I would like to do is which is actually very compatible. I mean, I don't mean would be to take only dependent sums. Then you have to introduce this delta 1 as an extra constant, if you want. That's a type, which is a special feature. And so a map out of that you call one cells or maps or I don't know. And then, as I said, I can come back to the very beginning. What I wanted to do. Yeah, here. You see, there is I would like to say that I would like a final object as well. So, and I would like to say that the final object, I will say we have a pullbacks if you want. So the fibrations in the classical, if you take the language of Joyal tribes, if you want, so you have fibrations which correspond to iso-fibrations for categories, and then you would like the dependent product from the disjoint union of delta 0 with itself to delta 1 should exist, because that would be the join operation, and that's a very central feature. And then you want also you have really a long list of axioms, so I can only give you the flavor, I guess. So the join operation you want also described in another way. So I'm assuming that if you know what are tribes and so forth, so in some type theory, you are supposed to be able to say what is homotopy pullback, homotopy push out, and so forth. And then you have to write down the syntax of that. But, so if you know how to say that a square is a homotopy push out, so there is another way to define the join that you can find also in the book of Lurie, that is called the fat join. And so the fat join of A and B, it is a quotient of A times delta 1 times B, produced by a suitable explicit push out square. And so to express this square and a comparison with the join defined by a dependent product, as I said, it's easy to see that I mean you can formulate that this join defined by the dependent product is actually produce a fat join as well. That is, you have to prove that some square that I would need the blackboard here, but is also a homotopy push out, and that is an important thing because if this is join operation, it corresponds to slices. And for instance, if you join a corner shape diagram and you join a point to it, you would get a square, for instance. And so squares are important because Cartesian squares are important if you do category theory and stuff like that. And the fact that Cartesian square, if you want to do the game of category theory, so you have Cartesian squares, and you want to interpret Cartesian squares as a particular case of limit also. And if you look at it literally, like syntactically, seriously, you will have a difference between these two things. And they will correspond to these two ways to look at the join. The join defined by the dependent product and the join defined as a fat join. And they correspond to these two versions. So the Cartesian square version corresponds to the dependent product thing, and the natural transformation interpretation, which would give you the description of Cartesian squares using the language of limits, correspond to the fat join. But all this you can formulate within type theory. And then using joins, you can define, you have to formulate what it means to have partial adjoints, but then you can define what are slices and stuff like that. And it means you can express category theory. Then of course, with what I said, it's not enough to prove theorems about category theory, but you can express statements. And then you can introduce the existence of universes, because then with this delta 1, what I forgot to say also is that this join operation, you have a type theory, so you can also express that you are zero truncated, for instance, that you have no higher sets. So you can also formulate the fact that joins preserve this property of being zero truncated. And then you can force the fact that you see the join, it's a way to produce all the simplices. Because as I said, so to do category theory anyway, in a way which is hidden or not, we need either the subsumes language or the cubical language. Cubical language means you take this delta 1 and you take a product with itself many times. Yeah, delta 1 times delta 1 and so forth. And then you have some cubical thing. Or the join operation is a way to go simplification. You take joins of delta 1 with points, and then, but then you want to say that you have the simplification operators. And then what you would do is to say that if you restrict to the, so now I just define delta n, I just join a point to delta 1 and see what happens. And then I can add a few operators, but for this you can use this in very low dimension, up to dimension 3, I think, or something like that. You can add the simplification operators and check that they have what you want. And then it will force that somehow the full subcategory of the delta n is a monoidal category with respect to the join. And therefore, by universal property of delta, you have all the other operators. And the point is that, but they will exist only up to equivalence, because everything is defined up to equivalence. So I don't say that you have a simplification object on the nose, but we have a simplification object which have the simplification identities up to coherent homotopies and so forth. But that is sufficient because the coherent homotopies will have a constructible space of. I mean, it will be some. So it will be a non-strict co-simplification object, but you can do that. And once you have this thing, you can express a Segal condition. You can express what is say the inner horn of delta 2, and then you can, as an axiom, if you have internal, you can force that you have internal horn and some dependent product, as I say, exists. So the map to the point have dependent products, say. So you have internal horn, and then you can express that you have the Segal condition. And then, as I said, you can express that you have universes and so forth. And then you go back at the very last slide, you can express that you have some form of univalence. And then the goal would be to prove what I said on the this slide. Do all of category theory there. That would be a goal. Yeah.
Thank you. That was very thorough and answered my question. Appreciate it.
Okay. Any further questions? Maybe I'll make a quick comment. It's not really that related to the talk, but I wanted to say that I scrolled through everyone's video feed, and the number of people touching their face is quite remarkable. So remember to wash your hands. Yeah, that's, as I said, not very related to the talk. But yeah, any comments more topical? Let's maybe wait a second. Okay, I'll just ask a quick reference question. So on slide 23.4, you mentioned this criterion. That's needed. Yeah, so in point 4, you get this equivalence of infinity categories. And so this is really, I don't know. So I know a reference for that in the fibration category setting, co-fibration category setting, which is your paper. But in the infinity category setting, I don't know. So I proved it when I needed it, but I don't know a reference for that.
So sorry, for which thing exactly?
So there's you deduce an equivalence of infinity categories from a functor that's an equivalence of fundamental categories and then preserves finite limits. Yeah. So in the fibration category setting, that's just I don't know. I mean, it's your theorem.
Yes. And for infinity categories, that's also true.
Yeah, it's true.
But that's also, there are several proofs of it. I don't know. I don't even know who did that the first. I mean, there is a proof definitely in my book on higher categories.
Oh, okay.
And there is another, which is something better in the paper by Kim Nguyen and Georges Raptis. And I apologize, but I forgot the third author. But they prove that even to have an adjunction can be tested on the one category. That's even better. And then as a corollary, you can deduce the equivalence. Because you see, if you have an equivalence, you have a quasi-inverse, which is an adjoint, and then you. So it's even better. It is on the archive.
Okay.
I will send you
yeah.
reference.
I'll look at
there are
that.
references, but I'm not sure they were available when you needed them.
No, this paper is still in preparation, so we just we couldn't find the reference, so we just proved it. But
okay. No, there are references for sure. Yeah.
Okay, so yeah, and I read your book, so
it is there.
so I just yeah. Okay. Any other questions? Comments?
I mean, maybe a comment. I just Googled, and it looks like Kim's thesis is on his website, so that's really wonderful. Thanks for making that so easily available.
And hopefully the paper in preparation should be available not too far away in the future. I mean, we have proofs, we just have to write down things.
And as we all know, that's the fun part.
Exactly. We have nothing else to do. So.
Yeah. Okay. Any other questions, comments? If not, then let's thank our speaker again. So another round of silent applause.
Thank you again for listening.
And I think that's it for today. So thanks, everyone. And we'll see you in 2 weeks.